Another draft physics video presentation. Draft science here on YouTube. Alright, comments. And I think I have another way to explain this, momentum thing. So, where to start? I guess we'll start up here with Martin Lee. Yes, you are getting warmer to the sense I'm drawing. So he's getting my point, I suppose, and he thinks I'm getting his. But we still are fundamentally disagreeing that this isn't critically, this is a real dysfunction to have two equations stating that they are qualifying or quantifying the same thing, and they have different answers. And the answers aren't a little bit different, the answers are dramatically different. And, there's just no point in not resolving whether it weighs 10 pounds or whether it weighs 5 pounds. I mean, it's not the kind of thing you should really have an argument about, is, something this obvious. So I have figured out some things about why this gets complicated. So you have a mass of 1 and a mass of 2. You have a velocity of 1 and a velocity of 2. So you have a light thing going twice as fast, a heavy thing going half as fast. And the question is, I guess I can write all the way up here, right? Yeah. You have one equation that basically says just multiply the mass times the velocity and you're done. And the other equation says that energy, with a K, like it's supposed to mean something, is 1/2 the mass. And then you times that times the velocity squared. Those two are obviously very different answers. So for these two objects, the kinetic and the momentum, would be whatever. Let's just say it's, well, we can do this. I mean, we can just say it's 3 here. Oops, no, it's multiply. That's just going to complicate things. Well, let's just give it an arbitrary number. So this one would have a momentum of 16, and this one would have a momentum of 16. But if you calculate the kinetic energy, this one has a kinetic energy that is twice as much, so it's 32, and this one would have a kinetic energy that's 8. Half. Well, let's just say 16. No, it has to be 8. Okay. And that's a huge differential, right? I mean, these two equations are obviously coming up with numbers that are very different, and, there's a truth here. Let's find the truth. All right, so my argument is this really just has to do with how well you can transfer the energy. So maybe we can get agreement on something. So I would propose that if I take both these things and crash them into the same spring, so we just crash them into a spring, then we just lock the spring where it's compressed. So however far they compress the spring, we just lock that spring. And then I just put the car on there, the opposite car, and I'll get exactly the same results back. So whether I compress the spring with this car, and then I release the spring using this car, or vice versa, I'll always end up with the same outcome. I'll end up with a car that's twice as heavy moving half as fast, and a car that's half as heavy moving twice as fast. Hopefully I said that the right way. So if we can have agreement on that experiment, and that's what the experiment results would be, confirming the fact that they both have the same energy. They'll both compress the spring the same amount. They'll both do the same amount of work on the spring. There won't be any difference. And the real conversation is about what happens when I try to transfer the energy using some mechanism that can't absorb all the energy. So if I use a mechanism that, like I just crashed the heavy car into the light car. Well, if I crash the heavy car into the light car, the problem is the heavy car is only going 6 miles an hour, let's say, and the fast car is going to end up going 12. So as this car hits the car that's moving 0, well, as soon as this car gets up to 6 miles an hour, this one can't push it anymore, right? It's moving as fast as the pusher, so half of the energy, so to speak, can't get into this car because this one can't push it anymore. I mean, it's just kind of obvious. As soon as this one starts to go faster than this one's going, and this one's starting to decline as it's hitting, so as it's transferring its momentum, so it has a momentum vector, as it starts transferring its energy to the other car, obviously this vector is getting shorter and shorter, so its velocity is declining, right? And this one's, its velocity is inclining. And so the number where it stops being able to send energy is going to be somewhere much earlier than half. So before even half the energy is into the other car, this car is already going to go faster than this one, meaning this one can't deliver any more energy. So that's the catch to this experiment, is understanding this is just about delivering and whether or not you can deliver your energy completely. In an experiment where you can deliver it completely, you'll get very different results than in one where you can't. And that's all this is about, is how you're testing the voltage. It's not about the voltage, it's about how you're testing it and whether you're getting it all. So the trick would be is that it sort of works if I use both these cars. So let's say this is another experiment we could sort of agree on. If I use both of these cars to push something even bigger, all right, something that's 3 masses, okay, and 1/2 of a velocity. So now let's say if this was going 6 and this was going 12, this one's only going to go 3. All right. Now you could sort of understand that if I use this car, I'm okay, and even if I use this car, I'm okay, because they're both pushing something heavier. And so they'll transfer all of their momentum, most all of their momentum, before this car is going fast enough that they can't, push it anymore. So most of the energy goes in. Sort of like the, the pool ball example, where you get a nice kinetic transfer because of the speed and the fact that the two bodies have the same mass. So it's much easier to transfer the energy. But if I make the weights disproportionate, then I get things that can happen. So if I make this heavy enough, both of these things will just bounce off before their energy can be transferred, because there's so much bulk that the energy has to be spread over that it takes way too long. And the reflections, that this thing starts reflecting the energy before it's completed pushing it in. So it hasn't gotten the energy in yet, and it's already reflecting energy back, and you'll end up with just a reflection. So it's really just about transferring, and the argument is if you do it, I should be able to get these people to agree that if I transfer the energy carefully and completely, that is, I use a mechanism that isn't time dependent, that doesn't care really how fast it's going, it just cares about how much it can push. And that's really all you're supposed to be measuring, is what's its ability to do work. How much work can it do? Not how fast can it do it. None of that's supposed to be important. Just what's its total capacity to produce movement. And that will find out that this momentum formula is the correct answer, and that this is is misrepresenting the real energy by just perceiving this to be just about how well you can transfer energy. And the fact is that speed gives you an advantage, and that's it. But it doesn't mean you have more energy because you can deliver it faster. The only thing that matters is what's the total energy. So this really is just about designing careful experiments, and the only reason why this kinetic energy formula exists is because they did some experiments that weren't very careful. And the fact is they didn't really measure actual energy. They weren't good springs. They were springs that gave advantage to things going fast and disadvantage to things that were heavier and moved more slowly, but delivered the same amount of energy if you allowed them the time to do it. Yeah, I think that's a good enough way to say it. Yeah, so I think that's probably a good enough description of what's causing the fact that you can come up with arguments that defend both these theories. But ultimately, I'd say this argument, where I'm asking you to try to extract the energy, will demonstrate that the only energy you can extract from either one of these is the momentum, and you can't extract anything else ever. Yeah. Alright, satisfied with that. Oops. Alright, so, yeah, the troll, John Wayne, left a couple of comments complaining that I should unblock the people who disagreed. There was only there's only one subject I'm conceding I was wrong on, and that's the subject of gravity, okay? And the fact that if you throw something twice as fast, it goes 4 times as high. And I'm conceding, yes, that's true. And it's also true that you have to put something 4 times higher to double its momentum. That's also true. So as long as it's that context. But I didn't block anybody on that subject. And, you know, there's even proof of it in the sense there are comments. You know, the comment by the guy who, you know, asked me the rhetorical question, do you know? That comment's still up, okay? I'm going to delete it now just because I concede I was wrong. So no point in me rubbing it in to myself, okay? But I did leave it up here. So I didn't block anybody for disagreeing about gravity. And so on the gravity subject, this YouTuber person just keeps arguing and arguing, and, you know, we're really not getting anywhere. And he's just not accepting that, you know, just like with relativity, that's just a fact that when things go a certain speed, you know, all of a sudden they have to say, well, you got to include gamma in the equation. It becomes relevant. Now, I'm making the same sort of argument. You know, instead of Einstein's argument that that things when they go fast get heavy, I'm clearly giving you reason why I believe it exactly the opposite way. Okay, that when things start going fast, they get harder and harder to push. Not because they get heavier, it's because you lose places on them to push. There's just not as much to push. So the energy can't hit matter anymore as readily. And that's why it takes more energy to move something faster, and theoretically it takes an infinite amount of energy when it's going near the speed of light, is because there's so little of the matter you can actually now hit, because most of the matter is moving as fast as the force you're pushing it with. Just like in the example I just gave. If the thing is moving away from you, if you're pushing something and it's moving away from you faster than you're moving, you obviously can't push it anymore. Duh. So that's sort of the argument. But anyway, so let's read some of this. But it's just a plain fact that velocity plays a role. Quote, okay, you keep restating the same thing, then accuse me of rewriting what you wrote. Well, you do rewrite it. You imply that I'm saying velocity is everything when I'm saying no, it's part of the story. There's a lot of factors, and mass, as I stated, is the velocity is essentially painted on the mass. I said those exact words. So you're choosing what to quote, and you're choosing what to emphasize. And maybe I could put things in better words, but I mean, I have said them 5 or 6 or 10 times, and you just keep ignoring them. I've provided you analogies and asked you to point out how the analogy fails. You're not doing any of that. All you're doing is keep hanging on a word and keep trying to bend it into something else and something I didn't say. So, you know, is there some reason for me to believe otherwise? I mean, is there, like I said, you don't deal with any of the points I've made. You don't quote any of the points I make. You just restate pieces of them. Okay, anyway. Just a little less gravity than you would experience if you were moving in the opposite direction. So I'm just making the point that if you're moving into a force, you're going to encounter more force, and if you're moving away from the force, you're going to encounter less force. That doesn't seem too complicated, and it just is sort of illustrated with this whole train analogy. You know, if you have some hope of running faster than the force coming for you, you're going to be affected less by it. Now, we can't run as fast as bullets, and we can't do all this kind of stuff, so we can't make that big a difference. But it's a fact that it would make a difference, whether you're running into the bullet or running away from the bullet. It's going to help a little bit. Once again, this is your assertion without any evidence. This is theoretical physics in the first place, some of it. And I certainly am citing plenty of experiments and going over why I think they're complete nonsense. So I've given you my explanation of the two-slit experiment. Now, the gravity argument is kind of a theoretical argument. All you can do is meet the existing facts. So I explain why this particle theory explains the inverse square law. I've explained where the how the energy is in fact quote-unquote destroyed, and that's why the Earth is radiating less energy than is going in. So more energy goes into the Earth than energy that comes out because the force is busy moving matter. It's a perfectly rational and sensible explanation, and what you have to do is point out why it doesn't work. You don't have to say, I agree that that's the right answer. You just have to concede that, yes, the existing evidence doesn't disqualify it as an explanation. All right. Since you are making claims contrary to mainstream physics, that doesn't mean I'm at a higher standard. So again, it's sort of duplicitous for you to start out by saying we automatically know conventional physics is right. No, it's just an idea, and the competing idea doesn't have to be better, just has to be just as good, at minimum. Which we use in our machines around the world. So it's more argument that somehow he has an experiment I can't explain. So again, that's just bullshit. So until you put up, you kind of have to shut up. So if you're going to keep saying that kind of horseshit, there is a point where I'm just going to block you. Because it's not true. You don't have any special evidence of any experiment or any machine that's doing something where you claim my theory fails to explain the machine. So show me the machine and then make your claim, but you just can't make it and just state it as if it's a fact somewhere that I have failed to explain a phenomenon, because I haven't failed to explain it. I've better explained it. See the two-slit video. I've provided more information. I've predicted more than they predict. Okay, it's up to you to demonstrate why we should abandon our formulae and use yours. Well, in the case of the two-slit, I would say it's exactly the same answer. So, the really complex math where you do the integrals over the 4 point sources. And I would just say my math is so much simpler. Why would you bother doing it the hard way when you could do it the easy string way? But beyond that, the underlying argument is that the theory, regardless of the math, right? Their math works. Their force source math works. I'm just explaining why it's 4 sources. It's 4 sources because the surfaces are the sources and the surfaces are causing the effect. So it fits my theory. And I'm pointing out that if your wave theory, it doesn't really fit because you have no explanation for why the wave, you could explain why a wave breaks if the surface is here. Okay, here's a surface over here. You could explain why the wave breaks here, but you could never explain why right here it just decides to break. The wave breaks right here. How are you going to explain that? This just doesn't make any sense. That in the middle of an open space, the wave would just spontaneously say, I'm going to break here. Become 2 waves. So I'm saying there's reason to doubt the wave theory, and there aren't the same reasons to doubt the particle theory because it explains it so much more completely. All right, well, anyway. The burden of proof is on you. Again, I can't do anything more than the regular conventional physics, except I won't do what they're doing, which is say neutrinos exist because we found them mathematically. That's a little dangerous. Okay, we decided we had a leftover. We had a remainder, and we decided to call it a neutrino. That's just kind of crap. So where has this burden of proof ever been met by your physics. I would argue you never even proved light was bent by gravity. You've had 100 years to do the experiment with better technology, and you never did. And especially the big transition was space technology, where the resolution is 400 times better. And you can go find the NASA engineer. I never remember his name. Sad of me. Damn it. Well, anyway, I mean, he worked with lasers at NASA for whatever, 25, 30 years. And he knows they never saw light bending outside the sun's corona. So it's just a fact. They got plenty of scatter, inside the corona, but they never got light bending outside the corona, which just kind of indicates that, yeah, without the particles, there's no bending. With particles, bending. No particles, no bending. So there's plenty of evidence if you care to listen to it or care to pay any attention, and there's certainly plenty of arguments to point out how your evidence is completely insufficient. It's well below the standard of proof. The Eddington experiment is well below the standard of proof, and if you can't agree to that, you're being pretty lame, in my opinion. It would be a lot better if you had that experiment repeated with modern technology, and you don't. Alright, mainstream has already met its burden, so says you. I don't think they've ever met the burden of superposition. They haven't met the burden of proving they sent a single photon through an experiment. They haven't met the burden of saying in the two-slit experiment that a place where light was going, a place that is bright, I open a second slit and it gets dark. They've never proven that. So, I mean, there's lots of claims they make. Never had a detector experiment, so all of those detector references are all fake and phony. So again, you're making a statement and you want me to believe it, or you want me to be persuaded. Or is your point just to say, well, I'll just make these arguments because we all agree with me, and all the people who agree with me will just sit there and like to pile on and say you're wrong, but we won't really prove it. I mean, if you're trying to persuade me, you should know that that's not a very persuasive argument. We say so. We proved it. I'm pretty unconvinced. Like with LIGO, you're convinced. I'm not convinced because theoretically I know they don't even know how a beam splitter works. They don't even know that the two beams can't be identical. Alright. Already met its burden of proof since we use mainstream formulae in our machines millions of times every day. So this is more of an allusion to somehow computers wouldn't work without quantum mechanics, knowledge of quantum mechanics, all this crap. None of that was part of the development of any of this technology. This was never something that was made by theory. Theorists didn't make computers. Theorists didn't do any of this stuff. They didn't make the first transistor. It's just a pile of crap. Didn't happen that way, and you keep saying it, but it has nothing to do with the truth. All you need is some knowledge that light scatters. The knowledge that light spreads when it goes through slits, that general knowledge tells you a lot. You don't need to know that, it's because the light's in superpositions and it split in two and it did this. You don't need to know any of that, to use the fact that the light spreads. So, you think that's a credible argument, that you can sit there and rely on saying, well, our physics created technology, when you kind of know that's really not the history. If theory worked, they wouldn't have taken 20 years to make a blue LED. To turn a red LED into a blue LED. It wouldn't have taken 20 years, if it's just about theory. All right. P.S. I posted a tangential question to this point, but I removed it in the edit because this discussion is long enough already and I don't want to branch off into a lengthy tangent. Yeah, just post it somewhere else then. It's not that complicated. But regardless, whatever, you can always email me too. The threading on YouTube sucks, so that's all unfortunate. I will tell people, if you post more than one comment in a thread, I'm not going to appreciate it. So if you can't make your whole comment in one comment, I'm not going to like it. I'm going to consider it rude and stupid, because the threading sucks. So it's going to get all broken into pieces. So don't do that. Watch a whole video, type one big comment. That's the way to do it. Don't type a bunch of little pieces of shit. Okay. So anyway, uh, you know, it's almost like we've lost the start of this conversation, which is an argument about Galileo, Newton, and then the French, Leibniz and whatnot, changing the concept. Kind of a reliable concept that said energy is basically momentum, Galileo, Newton, and then going to some new notion that somehow energy is this new formula. And I would just, again, argue that I don't think you have any way of demonstrating that the new formula gets the right answer. And that the old formula, there's no evidence it gets the wrong answer. Except the evidence that your new formula gets a different answer. So you're just saying the old formula is wrong, not because there was some reason to believe it was wrong, just because you're going to assert it because the new formula has to be defended. I mean, it's kind of hard because energy is this ambiguous thing, right? So it's kind of hard for me to just look at something and say, oh yes, that's 58 joules of energy. And that's, 74 joules of energy. So the only way we can measure it is with good thermometers. Now, you either accept or reject the argument that there are thermometers that are good, and there's thermometers that suck. And so I guess that's what we're really arguing about. So if you accept that there's different ways to test temperature, and some of them can fool you in the sense they'll give you the wrong reading if the temperature moves too quickly, let's say. Scales that can measure weight, and they can measure weight that changes, or I don't even know how to put it. Really appreciate the fact that maybe the clay experiments, maybe that wasn't the most brilliant way, measuring how much something penetrates clay, to measure total energy. Just like bullets going through somebody's head isn't a great way to measure, how far a bullet goes into your head isn't really telling you how much energy the bullet has. What's going to tell you that, is the velocity of the bullet and the mass of the bullet. That's how much energy it had. Now, whether it's in a form that makes a really nice hole, a clean little hole, that's not the point, right? That's not a definition of energy. The definition of energy isn't how clean the bullet hole is. The definition of energy is how much crap did it move. Yeah. You should just quote that statement. The definition of energy is how much crap can it move. And point out to me how that quoted sentence, how that isn't the accurate definition of energy. Because the definition of kinetic energy doesn't give you that answer. The formula for kinetic energy doesn't give you that answer. Okay. I think that's enough. Yeah. Let's see. Yeah, so this guy, some reason, didn't like the bowling ball bullet analogy. And I admit, I don't have that from some grand authority. I just have it from some knowledge of guns, some vague knowledge of how much energy a gun produces. And that if I was to use a gun to roll a bowling ball down an alley, I know, I'm not going to get much out of it. What I mean, a half meter a second, maybe, third of a meter a second. Gun's not going to be able to shoot a bowling ball very fast. So it's pretty much the same as me just, trying to hand one to you is probably the same energy as, 38 in the head. But anyway, the point is just obvious that, the energy is in different forms. It's not about how much damage energy can do. It's not how far it can fly. Those aren't the definitions of energy. The definition of energy is when you add up all the ways the energy is lost, how much energy was there, how much little pieces of air, and how much pieces of this, and pieces of that, and pieces of everything, how much stuff got moved. And that's really the definition. Now, obviously, when it moves into gravity, it's not moving any stuff, but gravity will tell you, because when it does hit the ground, when you let it fall, it'll give you the same energy back. So you can just look at the hole in the ground and analyze it for how much energy is in the displacement. But then we're back to clay experiments, and you know, it's not that easy. You know, like I said, you have to measure the heat, and then you have to measure the displacement, and you know, what else is there? Heat, displacement, movement. I mean, displacement just means you're taking matter and moved it from one place to another. Um, and I don't think there's anything. I mean, substantially, that's where most of the energy is going to be, is in those two forms, either heat or displacement. Sound and noise and noises, and you'll probably give off some X-rays and some other crap too. Anyway, that should be something we all agree on, and so it's, again, I don't know how. There really just shouldn't be an argument. All you have is the momentum vector. And if anything's going to change, if anything's going to get lost or used or wasted, it has to come out of the momentum vector. There's no kinetic energy vector to take it out of. Yeah, that's about the best I can do. Alright, so anyway. So, till the next time and such. Yeah, that's enough. Yeah, I'll do that. And say this was a draft science video presentation. Something like that.